mode.
Hey everyone, welcome. I'm Ken Clairbout, K4ZW, and we're glad that you could join us for our webinar. On behalf of the Worldwide Radio Operators Foundation, we're glad to have you with us. We've got an excellent presentation this evening or morning, wherever you might be. And as a matter of fact, I checked before we got started. We had 470 people registered, which is a fantastic number. So obviously a lot of interest in the presentation. A couple of things. I just want to mention that we will be recording this and it will be put up on the WWROF webpage maybe this weekend. And I would encourage you to go visit that, www.wwrof.org. Check the guys out. Look at the work they're doing, and they could always use your support if you're so moved. The other thing is we will be taking questions. You can submit your questions at any time, but we will hold them until the end of the presentation just so we can kind of keep the flow of things going. But you're welcome to send your presentation at your question at any time. And there's a questions box. Just type it in, hit send, and we'll pick it up and hold it until the end of the presentation. So we have with us JC N4IS. Also with him is Doug NX4D. And from down in Panama, we have Jay Hotel Papa 3 Alpha Kilo to help JC. So with that, JC, welcome. Glad you could join us. Go ahead. The floor is yours.
Okay, thank you very much, Ken. I appreciate our introduction, and thank you very much everybody that got registered and listened to us today. Well, we have several good news and things to talk about, and of course, I'm going to try to make this very practical, and I'm going to try to make real key information that you can really use. So we're here today. Basically, you see that picture here. It's a beautiful picture, original Waller flag, September 10, 2009, and that basically when that thing here started. I want to ask Doug. Doug, can you comment somebody how you can get started with this beautiful antenna?
Yes, I have a little presentation here I'll give. Good morning or evening, gentlemen. I am Doug Waller, November X-ray 4 Delta. My QTH is Central Florida. Here's an account of how the Waller flag, originally known as the Waller Adcock, came to be. After attending the International DX Convention's Top Band Forum in New Orleans in 1999, the 160-meter bug bit me hard. In the year 2000, I started with a 60-foot tower and no receive antenna. It was very difficult to hear any but the strongest signals on 160. I built a magnetic shielded loop, then a rotary diamond loop, then a rectangular foursquare with my home in the center of it. There was very little reception improvement, and I was becoming disenchanted fast with the top band. Then I built a rotary 14 by 30 foot loop, W7 IUV flag loop, and started hearing weaker signals. The flag had a very broad main lobe, so its best use was to place the rear null on my strongest local noises. Missing one new country after another due to not being able to hear them, I used EZNEC and eventually discovered that two very close flag loops phased 180 degrees produced an excellent pattern. The problem was the low gain. Eventually, I found that by placing one preamp at the feed point and another at the shack, I was beginning to hear some weak signals of the 160 very well. This Waller flag, as JC calls it, came close to not existing. The first test showed a poor signal to noise ratio. It was eventually discovered that the receive-only RCA plug had one ear broken off, allowing noise through that small slot, which is amazing for 160 meters. Replacing that plug produced some amazing weak signal reception on top band. After more improvements over the years, I am still enjoying excellent reception and presently have 298 countries and 40 zones confirmed on 160 meters from a 5th acre subdivision lot. I am totally convinced that 320 countries or better is possible from this QTH. I just need to live long enough for the DX to show up. Success with the Waller flag requires an excellent lead-in cable that allows no noise through the shield. I use Andrews Heliax with a solid copper shield for total silence. Proper RF choking, shielding, common mode braking, and grounding can give almost unbelievable results. My neighborhood is noisy, and I have had power companies out several times over the years to repair power pole buzzers. It is an extreme thrill to be able to compete with the big guns of 160 meters from a small lot. My greatest disadvantage is no room for transmit radials or a tall tower. I have missed 6 new ones due to their not being able to hear me calling them continually. It is my sincere hope that some of you guys and gals, if they are, will come away today with a desire to challenge this tough band and eventually conquer it. If you are already enjoying the top band, I hope this webinar gives you some ideas for reception improvement. I will be happy to answer questions after JC's presentation. Enjoy the webinar. Back to JC.
Okay, Doug. Thanks so much. Well, guys, can you imagine starting for little year on an RCA jack and almost threw all this performance away because you cannot get this thing working? So basically what we're going to talk today is how to get this thing working and what it does not work well. But like I'm Carlos and 4IS, and we are sponsored by the ex-engineer type from Team Duff that's supporting our worldwide Radio Operation Foundation. So let's start. Let's start defining what we're going to talk about. We're going to talk about high performance receive antennas in small lots. Okay, but what is really high performance and what is really a small lot? Like Doug said, here's actually his lot. It's a picture of his house. You can see here the Weller flag on this side of the house here, the beautiful Springfield Street, and here there's a little cross here is the top of his transmit antenna, is a vertical antenna. You can see when he turns the Weller flag almost takes the whole front yard. And this is 1/5 of acre, and for the ones not familiar, US is like 500 square meter. It's like 20 meter by 25, or a little stretch like 15 by 18 meters. So it's 500 square meters or 1/4 weight. So he worked like 309 countries for that specific location. And you see there is almost no place for radios also. He has a little creek on the back when he throws some wires in there, some radios is here on the driveway, inside the kitchen, inside the other place. I don't want to say where you have the radios there, but what you see here is a vertical and it's top loaded. That X on the top, it comes to the wire and hangs around the X. It has even no space for an inverted L. There is no place to put the horizontal thing. So, but Doug also started in 2003 with that antenna, but only in 2009 he got it for his own. It's pretty quickly. If you think about that performance, we talk about 2 new countries every month. If you keep doing this, maybe you get 24 every year, but you need to keep doing this another 13 years in a row. Then you can get more information on his website. Here is the link. So that's what we talk about performance, right? Constant in performance, delivering performance, digging with weak signal. So that's what we're going to talk about today. We're going to talk some base concepts, what makes that antenna special, what makes a receive antenna special, signal to noise. We're going to talk about some new antennas that we developed since we started with this project. And also on the back, you're going to see more information that I won't cover today, but it's going to be available on the presentation. You guys are going to receive, Ken is going to send the actual presentation for you. So you have a chance to get more information and maybe send emails or ask more questions for us. So really, basically, directivity and gain are 2 different things and very confused. I want to try to make this thing a little more clear. So everything about weak signal on 160, and 160 is a weak signal band, is signal to noise ratio. So basically what you need is a signal 3 dB above noise, or for 8 dB for sideband and 3 dB for Charlie Whiskey for code. So here we are going to represent this. You see from spectrum, actually this is collect from audio, and you see here the signal and the noise, and here this bar, 10 dB each bar. So when you hit the waterfall, you can see even there is one signal buried at the noise level. Here you know the signal is here, but actually you cannot hear. So, and here's the signal at noise level. As Doug mentioned, we almost lost this project because all the receive antennas with negative gain, negative power gain, needs a preamplifier. So this is the first thing, that we get two amplifiers. You put one in the tower, another in there. But what really the amplifier does for you? So the gain is really a difference with the signal input and the signal output. And if you have a signal like that one, that is like 28 dB above noise, and you put 18 dB preamp, the signal is going to go up. You see here another bar, 2 bars, so it's 80 dB. But what happened with the noise? The noise goes up same way. Actually, no, exactly. Every single amplifier has its own noise, and anytime signal passes through an amplifier, the signal-to-noise ratio, the output, is always small in comparison with the input. So it's our degradation that we call noise figure or degradation or merit, figure of merit. Is all electronic amplifier are not perfect. So amplifier is really not solution. So how we can get more signal to noise ratio? Actually, here one example is actually a signal I measured for a carrier in 1840. I had a spear in there coming from east, and the signal was 30 dB above signal noise, above noise with my transmit antenna. When I moved to my Weller flag, I recorded here 40 dB. So the same signal, just listen one antenna, listen another antenna, you can see the difference. And that's the key, really the key point. If you want to dig signals out of the noise, you really need to look into signal to noise ratio. But if the signal is above noise, and you're going to start looking to different antennas, try to do evaluations, how the antenna's performance, how we compare, you really don't compare anything. If the signal is above noise, you just be a little comfortable, but the radio is going to sound the same. And a good receive antenna is the one that you can dig the weak signal out of the noise, signal that you cannot copy on the transmit antenna and easy to copy on your receive antenna. And measuring this signal to noise ratio for several years and really dealing with different antennas, I come up with the measurement. Every time you increase 1 dB of RDF, the impact on signal to noise ratios is 1.5 to 2 dB. That's very important. This is really measured. It's not calculated. It's not a magic formula. Just testing and testing and testing. You get that number, and I see very consistency on this. So let's understand what really means directivity. Actually, every antenna has two very important numbers. One is directivity gain, how much energy you can concentrate in front of the antenna, and the other is power gain. But most of the antennas, aluminum antennas and transmit antennas, has very efficient, and power gain is normally 1. Everybody say antenna gain, but actually there is 2 different measurements. The directivity gain is really, if you think about space, you need to think about signal coming from all directions. Like in the case you have here vertical, you have a representation of the diagram of the vertical, and of course the vertical is a good transmit antenna, but it's one of the worst receive antenna you can build. You can see here like noise from everywhere, but the DX signal coming for just one direction. The only way you can improve signal to noise ratio is with directivity. If you put a antenna with directivity and you replace all that surface here with this new surface, you have a lot of attenuation, different directions. To evaluate antenna, you really need to think about 3D, about space, about things coming in all angles and directions. So it's really about the ratio between the, let's get back here, about all that surface here and how much attenuation you have in each one of those square against the little area here where the real DX coming. As much as you narrow the directivity, you have more gain. So this is the directivity gain. And that's the only way you can improve signal-to-noise ratio. There is no other way. Anytime you put a preamp, you add noise, you put a filter, you add noise insertion loss, go right into the signal-to-noise ratio. Of course, you can do some calculations and DSP or things behind, but you already have the signal there. So the only chance you have to really dig some signal out of the noise is with directivity. And WHJI makes this very popular, calling like receiving directivity factor. But actually, this is something very well known in terms of antenna gain, power gain. If you go to Edward Jordan and Keith Bowen, book in 1950, a lot of guys used that book as a test book in graduation college. There's a good explanation of that. But mainly, the RDF is the difference between average gain, or the gain all directions, and the gain of the real signal you want to see. So if you use EZNEC, other programs also exploit this in a different way. But if you put in 3D, you can see here on the bottom the average gain. If you don't use 3D, you won't see that. And then you get the maximum gain from the model you're thinking. You just use the calculation. You get the RDF, or receiving directive factor. But what it does mean exactly? Let's see if we can understand what RDF can do for us. I put here a list for 5 to 12 different antennas. Then you see like the vertical is really the worst receiver antenna you can have. A little better than a vertical is come the magnet loop. And then you see the inverted Vs, K9AY or flash, going to talk a lot about that. Bog, 400-foot bog, not much directivity. Vertical flag, little dipole. Dipole has also directivities. It also has some directivity gain. And then you start getting into 10 dB or 11. You start seeing 4 squares, Waller flag, Beverage with 1,000 feet. Also here in between you see the shared apex loop for resolution, good antenna, 9 dB, close to 9 dB. But everything has different characteristics, like the dipole takes a takeoff angle 180 degree. The directivity, but is up, not so much usable. Beverage and horizontal flag at 40, Waller flag at 25, and vertical array really low angle, so very good for DX. So how exactly we can understand what it does? Let's compare with something we're used to in HF. So let's see what a 2-element Yagi can do, or you see the 2-element Yagi here is like 11, almost 12. Cubical quad, 3-element Yagi, but those things are a little complex. So you can look more. I don't want to pay a lot of time on this, much time on this. Leak, KT, TGR has a nice comparison chart, a lot of information, this link. I enjoy to see there. But let's go deep what really RDF can do for you. Okay, so normally you're going to improve something better than your transmit antenna. First step normally is a flag, a UOK9NY. Actually, you're going to learn later that this is really a loaded loop. They are almost the same directivity. And if you look at the diagram and you look in space, you're going to see that the noise rejection is really that part on the back. So I put like the 10 dB line, so that line cross from 0 to minus 10 dB. And this how much noise is rejected. If you think in 3D, you can see here the picture. And here one thing very important. A lot of people loves front to back. It's very easy to measure. It's touchable. You can detect, you can measure. But really, in terms of improving the capacity for you to listen a weak signal, does not help at all. So you see it's a very deep nu on the back. If you specifically has a power or line noise or somebody coming from here, you can see some stuff. But really what matters is all the noise coming from all that volume on the back. So transmit antenna normally has 5 dB RDF. We're going to use like a reference. And this is the noise level of a transmit antenna. And if you have a DX very weak, like 3 dB below noise, basically you cannot hear that guy. In another DX, this 3 dB above noise, then you can copy. So it's a two situation, one DX1 at noise level, another DX2 above level, so you can copy. So if we move from the vertical to flag or U or K9AY or similar antenna with just one loaded loop, you have 2 dB increase in directivity. That means 3 to 4 dB improvement in signal to noise ratio. So the noise floor for the flag is really around here, 3 to 4. Now, if you move from the vertical and compare to one flag or one U or K9AY, you're going to be able to copy the X1, some difficult, but it's 3 dB above noise, and it's very easy to use the X2. But that's a huge difference from the vertical antenna. Really, a difference between you can copy the guy and one antenna, you cannot copy the guy. So that is huge. But how we can do better? Second step, normally you go to phasing systems like DHDL with 2 loops in phase, or shared apex loops, those 2 loops in phase, or you go to horizontal flag. Those kind of antennas give you between 8.5 and 10. So if you look at the diagram, you see the rejection of noise goes almost 180 degrees. So everything behind this 10 dB line is going to be rejected. You already see a better elevation plot. You always need to think in 3D. So if you look at DX, there was a noise level, the transmit antenna, and the other DX we saw before. And now you go to a different antenna that has 4 dB RDF better than the one before. You really dig into the difference between the noise floor on the receive antenna and the transmit antenna is 8 dB. So if you have in this situation a weak signal that's only 3 dB below the flag, right? You cannot copy, but with the new antenna, the second step with the increase in 2 dB in terms of RDF, then you can copy the signal. So that's a huge difference that the guy with the vertical don't see anything, so what's going on? If you look at weak signal and you're using a GHDL or antenna with 10 dB, the signal is above noise, so it allows you to copy. So that's really fantastic. And if the guy only compares the vertical, you only get his frustration. Worst thing you can do is just receiving your transmit antenna. Is the signal that you want to dig and work are everything here below the noise. So, but you still can do better. What even better? So if you go to a 4-square receiver array or a Waller flag or a Beverage that runs around 11.5 and 12, you can see the diagram. So all the noise reject from the back is huge. So you see now only this 120 degree or something here really get noise in front of the antenna. Most of the signal is concentrated in here. So narrowing the directivity really gives you a much better signal to noise ratio. So if you go to 11.5 means 6.5 dB. So the signal to noise ratio improvement can go up to 13 dB. So it's a huge difference. We talk about the original noise level from the HDL up here, and now you go way down on the Weller flag. So 13 dB difference between the transmit antenna and receive antenna allows you to hear things that everybody else cannot hear with normal small receive antenna. So it's not really about front to back. So actually there is several ways to optimize the antenna, and if I get more RDF like 12 dB, I really damage the front to back. But it doesn't mean anything. What really means all that noise was canceled from the back of the antenna. So in this case, if you have another weak signal, and believe me, most of the new countries, you start hearing above noise is weak when it's working first. Always increase when you work it in, but that's the way it goes. So this DX3 signal, there was a noise level with the flag, a single U, and you had a better copy. You almost can do a QSO with a HDL. If you go to a 11.5 dB RDF, it's really comfortable because you're like almost 10 dB above noise floor. But with the Weller flag, you can copy the other ones, the little small one, and this is really unbelievable. You can really start working things that people can hear with the other antennas. But there is another way to improve. Rotation. Rotation is something interesting. It's like if you have a signal at noise levels from 0 to 3 dB, and here's the diagram. Normally you have those two lines. That means when you get the 3 dB line, when you get from 0 to 3, like if you go 1 or 1 dB, you start losing degradation in terms of capacity to copy. You are below the 3 dB threshold. So it's really interesting. You can deal with those two, and you can change their null, and sometimes you can just get a signal that you can put in this null. But really, if you go 74 or 80 degree, there is the front lobe. When you get the 3 dB, the signal is really below the noise, like here, right? So giving the capacity to change the directivity and adjust 10 degree or 20 degree in one side, you can use those nulls and improve the signal to noise ratio. So this is really an improvement. But it's also a different way to improve the receiving. If you go to what cancellation mode or man-made noise rejection. When I move the antenna for horizontal, several things happen. So here is the diagram. You see it's still low gain, but this red is the vertical pattern, and the green is the main pattern. It's horizontal. So if you have a vertical signal, you see a deep null in front. And that was a big step for me because I was using the Weller flag and a good antenna, but if for some reason you have power line noise in front of the antenna, you're going to hear the power line noise very well, right? So what about the noise of the city? How I can remove that thing? So the horizontal Weller flag allows you to go that way. It does have a big difference between horizontal and vertical signal. So the vertical signal has additional 30 dB attenuation. And what exactly does it mean? So it doesn't mean that you still have the same RDF. However, you're removing another 10 dB or better in terms of noise floor. So your noise floor normally goes like 22 dB below the transmit antenna when you remove the vertical component in terms of city noise or man-made noise. We're going to talk more about that. And then you become very comfort to hear the same DX we heard before. And of course, now you can copy really weak signals way below the traditional Weller flag. So what I see and measure here most of the time is that on the horizontal Weller flag, I get like 10 dB improvement signal to noise ratio. So you can hear things that nobody can hear because of that huge things. But how you keep that noise low? That's what we're going to talk about. And imagine using horizontal Weller flag in digital mode. So you can have digitally reduce the bandwidth, and you can have another 18 dB. So it's a very powerful receiver antenna for digital modes. So where this thing really come about was not really my idea. I was looking into stories, and I found these patents. And actually, it's very interesting because Harold Beverage in 1941, 1938, he patented for RCA a loaded loop. This was really everything started. It is a wire with a transformer and a resistance. It can be rectangular, it can be diamond shape or any other shape. You see the diagram here. And also he come with another patent with phasing. So you see the phasing, end-fire phasing. So this idea is here for a long time, but when they start, really went to military applications before the Second War, and a lot of people lost sight of those things. And really, Weller flag is really a Beverage antenna, and I learned this a couple years ago. So all these antennas really a loaded loop. I mean, a wire will transform it in a resistor, and then you phase them. Exactly, that's the same. But the difference is how you put them together and get the most signal-to-noise ratio, increase the directivity. Front to back really doesn't mean much. So here's how it looks like a horizontal Weller flag. Looks like a 4-element Yagis. These are the loops, the 4 loops. That one is 40 foot or 26 foot elements. So the elements here is like 26, 13 each side, or 8 meters. So what I did with that antenna since 2006, I heard over 299 the XCC, almost 300. I worked 282 and only 39 zones. I heard zone 23 3 times. I was not able to work. But this give average almost 30 new counts a year. So of course you can see about performance and how you can go in terms of digging signal out of the noise. So it's really serious business in this thing. But let's understand more what is a horizontal Weller flag. So first thing first, you're going to try to measure. This is a program I recommend. I use a lot from our friend Golf 4 Hotel Fox Kilo. And it's a program you can take the signal out of the sound card, and you have a source, transmit a signal, and rotate the antenna, and you keep the timing, so you sync the timing of the rotator with the antenna, and he plots the antenna. So this is actually a plot collected. So it's a signal during the day. A friend of mine, W4 Bravo Papa, a few miles here from me, sent me a horizontal signal in 40 meters, and I was able to take that plot. So it's actually measured. It's not a program. And here are other measurements for 40 meters. This for NHPR, like 5 miles away. This is another one. I took it at PT9 Zulu Echo. So this actually measurements. And it's very difficult to evaluate antenna if you don't have the right tools. So first, you need a signal come from one signal direction. If come for 3 or 4 different directions, complicated, like a vertical signal can reflect on towers, can come from different places. And horizontal thing is very complicated. We're going to talk more about that. So this is 40 meters, and this is a plot, the only one I was able to get on 80 from PT9 Zulu Echo. He has a 3-element Yagi, and I used to plot that one using Polarplot. Is actual measurement on 80, and this is the best plot I got 160. You see on that chart here is using 1700 megahertz. But hold on a second, does not look like something usable. Well, but that's because I'm using a vertical signal. It's very difficult to evaluate a horizontal antenna if you don't have a horizontal signal. And 160, that's really difficult. So this is really, what you see here is that red part of the pattern of the Weller flag, horizontal Weller flag, the vertical component, because you're messing with a horizontal signal. So what really is a horizontal Weller flag? It's a loop. A loop has something important. It's very small in comparison to the wavelength, but it radiates on the sides. There is two lobes on the sides and big dips from up and down. So really, there's a big attenuation on the top. There's some very different characteristics. That is, the takeoff angle does not change because this cancellation for up and down. On the center of the loop, it only receives on the plane. Does not change much when you have above ground. If you have this thing take off at 45 degrees at 30 feet or 100 feet, it's going to be the same. Or the important thing, does not change directivity with size. You can make a small loop or bigger loop, and the directivity is almost the same. So if you take a Weller flag with 10 feet boom or 20 or 40, the directivity is the same. It does not change the frequency. Very different from the Beverage. Beverage is wavelengths. Is a antenna when you go from 160 to 80 narrows, and from 80 to 40 it's become 2 wavelengths, and then change the gain and become very narrow front lobe. The Weller flag is always the same, and it's a non-resonant antenna. If you have here 4 meters by 4 meters or 10 foot by 10 foot or 15, is always the same. That does not have any resonance. So because there is no resonance, there is no interaction with other antennas. You can mix with Yagis, you can mix in place that normally other antennas won't work. And because you have this isolation between polarization is really 27 dB isolation between other vertical structures. But what does change is with gain above ground. That's important. When you have the antenna, people ask me, what is my antenna 50 feet or 100 feet or 200 feet? I put a chart here, and then you can see clearly if you have antenna 60 feet, right, and you are in 40 meters, like you're half wave above ground. So half wave, you lost like 0.8 dB. It's not much. But if you talk about 160, right, then in 1/8, you're going to be right here. You're going to lose like 12 dB. So if you have an antenna for 80 meters at 60 feet, 1/4, the only negative gain is like 1.7. You still can do well. But of course, for 160, you need 90 or 100 feet high. So it's a kind of trade-off between gain and how high you can put this thing. Of course, put on top of a high build in a rooftop, that thing goes really well. So mainly the horizontal signal, when it reflects, there's a bump grid, and here's the reflection, has something very important, different from the vertical signal. The horizontal signal has a component reflected 180 degrees, so the signal is negative. It means there is a cancellation. So every horizontal signal near the ground has a cancellation for the reflect signal. Actually, Kai for PT put a very interesting article I recommend to use on KSD and QRX about the intensity of the signal. So you have two components. You put the antenna high or low, you change the gain, but also the signal itself changes with high. So that's why we don't have like ground wave horizontal polarized. Everything is canceled here. So you don't have ground waves vertical. So this signal here, right, is a result of cancellation. As far as you go from this point, is increased. So you can see here the optimum gain for a horizontal antenna increases when you get high, but for the vertical antenna, it's just the opposite. When you increase, it gets lower gain. So talk about noise. This is how normally what you hear is the man-made noise. 160 is a very noisy band, and you have a lot of noise floor here. So 160 for residential area or urban area, rural or quiet rural. You see those things very popular. And here's the noise floor of the receiver. So you see that even 160 on a very quiet place, you still have a lot of noise above the noise floor of the receiver. But that mainly is vertical signal. It's man-made noise. Man-made noise is ground wave. If you talk about ground wave is really vertical, so the water flag can knock this thing down another 30 dB. So it's a way you can have a good receive antenna in a residential area. But an example here, some power line noise, a couple of miles far from my place, get huge intensity of the receiver. So 1.7 mile, like almost 3 kilometers, can put like S7 of your receiver. So that's why I moved to horizontal, because you have a very good vertical antenna, but you have an intensity of noise like this, and you move to that direction, the X in that direction, you cannot hear anything. So if you talk about skywave, right, and how the noise plays in terms of skywave, if you remove the ground wave, you just let the skywave. The skywave noise is difficult to measure. Here's some of the measurements. And also you can find here on Edward Jordan, also in ETUP 372. And it's very interesting because you see 160 meter here, right? It's very noisy most of the time, but when it's quiet, it's really quiet. Actually, it's interesting. It's quiet than 10 megahertz. It's easy to understand. Like propagation is better on 10 megahertz, but skywave is mainly activity from weather, from thunderstorms, from atmospheric noise. We don't have cosmic noise on low bands. So when it's quiet, like winter, 5% of the time. It can be low as 100 degree Kelvin, so like 1.3 dB. And on 10 megahertz could be lower as like 9. The thing is, here's on top, a lot of noise is summer, but we don't do DX on summer, do DX on winter. So in the winter morning, when the thing is really low, what really needs is a very low signal. And to match that signal, the system should have a very low noise figure. It's a kind of concept that people don't link with receive antennas because don't pay attention on skywave. Just look into ground wave. But when you remove the noise from the city, that's what you get. So to make this thing work, it was necessary to develop a system that very low noise figure, like 1.4 dB. So I use a 7800 with 20 dB, so with the preamp at 0.5 dB with 40 dB gain and attenuation on the filter, need the filter in front. You really operate near the receiving noise floor. And that's the thing, it's beautiful to have 22 dB increase in signal to noise ratio, but now your systems operate near noise floor, and that's where the things start, how complex is to keep that thing. So shielding, grounding, isolation, common mode noise is critical. The weather flag itself does not fix this, and this is where we need to talk about care. A lot of people implement antenna and don't see results. Like onion or noise is like onion. When you remove one level of noise, you get the second level of noise. So the local noise, if you remove the local noise for man-made noise, you start getting to leaking from the transmit antenna, reflecting noise from other towers, and you go into front-end noise until you really get the low weak signal down here. So until you remove all that stuff, you can use it. So here's like my vertical wire flag 60 feet far on transmit antenna, and here is a jumper that I can put on the skirt that detunes the antenna. And measuring the antenna, here's a measurement from the antenna with the transmit antenna not detuned. And when I remove the detuning, this is the diagram. So you see that's completely useless. So detuning vertical structure nearby is really degrades radiation pattern. There is no way, even if you are like 1,000 feet away from 160, you really feel wavelengths and can impact your vertical signal. So interaction is very interesting because when you have an element like a Yagi close to half wave, you have current, that's back here, inducted between the elements, and maximum near half wave and minimum near 1/4. So anything near that size is going to reflect signal. Like you have a 10-meter dipole, a 10-meter Yagi, and you have a 40-meter cable. Guess what? That cable is really have a common mode current that generates field and re-radiate noise. So if you have a transmit antenna near you're going to see this almost interaction deteriorating your antenna with radiation. So detuning these antennas is a must-have. You cannot get performance if you not care about the tuning. In case of horizontal wire flag, it's a little easy because you have a 27 dB isolation in terms of vertical components. So it's very easy to kill receive antenna. Just put a low dipole or a quarter wave elevator radius, and this thing radiate noise, you're going to kill your receive antenna. So what really does, if you think about the preamp and all the things that show up in the input, you're really mixing that thing. If you have common mode noise and you have transmit signal leaking into the receiving, you start getting things like this. Like if it's 10 dB, the diagram is going to be like this. So you don't see the bottom. Then you increase the signal. Then that's the kind of diagram you're going to see. Some directivity, but very low attenuation in the back. And if you're leaking more, then you completely lost everything. So it's very easy to let this thing leak, and then your beautiful diagram become actually like a vertical. You don't see any difference. So RDF is beautiful to get, but it's very easy to lose if you don't pay attention to things like open frame relay, plastic box, open shield connectors. That things can kill you in front of the receiver. Think about the preamp is part of the radio, not part of the antenna. If you don't think about every caution you need to build a radio, and do not use it on your preamp system, you're going to end up with this, no directivity at all. In all your effort, a lot of people fail to implement this antenna in the last 10 years because don't care about those little things. Shield, open frame relay, and basically the tuning. So here are two examples. Fred, PY2XB, lives in a city. You can go to the website and look. This is the tuning circuit for his inverted V and also his sloper. Detuning his antenna, he actually get 2 SUN improvements in signal to noise ratio. So he has a horizontal Waller flag. Normally he get 10 dB increase because RDF, but he was not getting the other 10 dB of removing noise because of the interaction. When he put this thing, the noise come in 2 SUNs. Doug was the same. He has the tower, and he has a detuning circuit on this tower. When he's removing the detuning thing, the noise goes up to 20 dB. You want to comment something about that, Doug? Are you mute?
No. What did you ask me?
About the detuning on your transmit antenna.
Yeah, all you do is you just use a wire that stood off of your tower and parallel it to the top and ground it at the top, and then you put a tuning capacitor between the bottom of the wire and the tower itself. And what you do is you create a resonant loop which prevents the tower and the wire from rebroadcasting signals. And when I did that, I had already been disconnecting my tower from the center conductor of the coax when I received, and that helped some. But what really helped was throwing this detuning in, and from 90 degrees to 0 to 90 degrees with the WF looking in the 180 degree quadrant toward the tower, I was getting from 1 to 2 S units of reduction in noise when I was receiving. So it's huge, especially if the WF is looking in the direction of the tower. It doesn't help much if you have the nulls of the WF, like if you're listening from west to north to east, with the tower being to the south.
Yeah, so I mean, 2 S units is a huge difference and makes you can get 2 or 3 levels of weak signals out of the noise. So protecting the feed lines is very important. So you have a coax, it's grounded here. So you have the common mode current that runs outside the cable running into the cable. Any electrical current on the cable generates magnetic field. So you have here a rotor cable, something running parallel, and the magnetic field generates another current on this cable, and that current generates magnetic field, and there you are, your common mode noise from one side go to the other side. So grounding is something good for protection, but in terms of RF, it's not enough. Like in an example, in my case, I use, here's the grounding, here's the transmit antenna, the other antennas, I can hear noise, but my receive antenna runs inside a conduit, a metal conduit. So you need to protect the receive antenna against those magnet fields. So, and also, when you look into outside, when I have all the antennas going to master ground outside, this is my transmit antennas, my receive antenna is also grounded here. I have chokes. Chokes protect to have a common mode noise coming to the receiving system, but I run inside metal conduit in here. This is not expensive, very easy to buy. Regular galvanized steel, cannot be aluminum, cannot be PVC. It's just to cut magnetic field. Magnetic field is a big problem because it generates more common mode noise. It's how the things transmit. So if you have a station like this, or like this, an example, you can experience different kind of performance when you look into this. So it's all hard work pay off. You need to remove layers of noise, one each one. Common mode noise is really important. Same thing with shield. All the preamps inside the shield box. There is no reason, any reason to put a preamp at the antenna point. Most of the cables on low bands has 0.5, 0.1 dB attenuation, but you need to move the preamp near to the radio. Remember, the preamp is part of the radio. and you need to have protection about magnetic field. It must be shielded. So things like this, very common on the internet, open frame relays, easy to build weekend project, does not work in low bands. You're gonna kill your reception doing this kind of thing. You can have a lot of noise that's gonna cover your weak signal. The benefits of RDF is gonna go away, and you're really gonna lose your time. So like this example on my desk with all the chokes and things like you see an EZNEC connector, chokes, and everything is shielded. This is my SDR that I use, a Quicksilver SDR, is choked. And here I was not choking like the USB port going to the SDR. When I put the choke here, I saw a lot of bursts just disappear from my screen. So it's a lot of hard work. It's not just the antenna. You need to implement the whole system. You need to take care of these things. So here's some progress. So I start with some Nortons and move into what I have today. Really low noise systems with a lot of chokes and good connectors. And that's the thing. Remember we started the story about RCA with earpiece broken? That's here's true. If you have any place that noise can come in, you're going to lose your receive antenna. So here's some good ideas about chokes. One example of how to build one, and you could go, and I recommend you read Steve Dove, Whiskey Echo Echo Echo. It's have nice information about how reducing noise on receive antennas. And of course, you need to talk with Jim, K9 Yankee Charlie, and also Chuck with beautiful articles and examples. But mainly it goes like this. Common mode noise runs outside the shield. It's a current outside the shield. Any place you open the shield, the noise gets inside. Choke is your best friend. So if you look at these two chokes, very popular projects. But that one, you see those opening here, can kill your whole system. And you don't know why your antenna does not perform. So really, you cannot go that way. If you open the shield, the noise comes inside. And all your effort is going to go away. This kind of project here, there is no cut on the shield. There is no little earpiece broken that the shield can come inside. So I choke everything, even like my AC line. This is how I build the AC line, overkill, but you don't need differentiation chokes on the AC line. You need common mode chokes, right? In this case, I come with 220 and I have an isolation transformer. And then goes to 110, that goes to the other things on the radio. So, but one thing that's really important, I'm following several guys installing antennas, and most of the point of failure is always there on the connect, on the braid. So PL259 is a really disaster. Please use clamp on, good contact, or better, go to N or SNA. Those connectors nowadays is less expensive than this here. There's not much CB, but a lot of Wi-Fi and things on microwave, so it's very easy to move. It's time to move, use new technology. Forgot about that. A bad connector can increase noise 2 to 4 dB, just one blade. So, and this thing cannot be so complex. We're talking about a lot of things that could be complex. But in the example, this PYRO is living in a townhouse, he's put a vertical for 40 meters. Was not listening anything because the S9 plus 10 noise on the city. And he wants to do some CW. So I sent him a choke and a resistor, and he put together his Weller flag. It's actually very simple, just one loop, and runs with twisted pair for 100 ohms Cat5. You just open the Cat5 and take the feed line. And this is bamboo, really bamboo. It cannot be simple. You pay like $5 to build that antenna. With that receive antenna, horizontal Weller flag, one single loop, cancel the city noise. He was able to work over 200 countries in the next 6 months on 40 meters. So for a lot of guys, that's the difference between you can hear or you can be frustrated. So playing with directivity is easy if you follow the system. You look at everything. Like twisted pair does not have common mode noise. So it's a big thing. If you do a U or a flag and use coax, chances are your coax is going to be a vertical. If at some point you put a choke or a plastic box or a connector that's open, the noise is going to come inside. And everything I told you that is beautiful, 22 dB and signal to noise ratio is going to go bananas because you let the noise coming in, right? So that's it. Oh, not really. We still have more to come. Hold on. We can do better. Like my friend in HPR, Pete, come with an idea. Why not tilt the antenna? So he put his Weller flag. He put a system here that he can tilt around the X. So he can have horizontal or vertical or play with that thing. And we're experimenting this. Experimented this 1.5 years, I believe. And like Fox Tango 4 Papa Alpha Amsterdam, I believe, he was able to work at 45 degree only, but not 45 degree, only the right side. If you put 45 degree on the left side, there was nothing there. It's not just going for 45 degree. You need to match the polarization. So he was able to work the DX because he matched the polarization. So we are working on that thing, and we still have more things to do. We start playing right now with 4 loops and using SDR for beamforming. With more directive, you can go to almost 14 dB RDF. Like in this example, how narrow you can go. And with SDR, you can beamform and maybe have a small. Today we are working with 70-foot booms. Maybe in a few years we can improve the SDR technology with beamforming. You can go maybe 20. We don't know. We still need to work. There's a lot of stuff to do. But if you don't care about those things I mentioned, common mode noise, the tuning or transmit antennas. It's not about the antenna, it's the whole system. Where you put your preamp. Preamp is part of the radio. You need to care about all those things, right? So you enjoy 14.2. It's like have a 5-element Yagis on 160. But you need to care about other things. The tower is 50%. The cable construction, preamp structure is another 50%. So look how much noise you can reduce that way, right? Only see the signal here in front of the antenna. So, conclusion, noise is up, unfortunately. LEDs, VCR cars, and what really difficult is most of the talk today was about noise coming from your neighbor, coming from your city, but really today most of the noise is coming from inside your house. Fridge, I saw some stations where the fridge generates so much noise it's almost unbearable. You need to turn off the fridge because they use those variable phase drivers and reduce the size of motor. And instead of $50 they can build a rotor for 20. They still sell for 50, but they can spend 20 and you get a lot of noise. So nobody has room for beverage, or even vertical does not work on city. Even the vertical Weller flag is excellent, but noisy. If you have noise source, you point to the noise, you're going to hear noise. So horizontal Weller flag is a low noise, practical size, but you need to care about all the other aspects that I mentioned. Common mode noise, noise figure, shield, and connectors. Don't mess up with connectors. It's the easy way to destroy your whole system. So here what we say in terms of performance, you can go deep as 300 countries in one cycle. I think this is huge, living in an urban lot, and for guys that lives in the city that normally has S9, like Freddie, Brazil, and other fellows I can tell about, like Sergio and other, they're using this antenna. Like Sergio PP5 for Jolly Radio. Sergio has his contest station, his house in the city. He told me he's very happy because in the last 6 months he worked almost 300 DX on 80. In only 10 he was able to listen to a transmit antenna. So invest on receive antenna today is a must, and noise is up, and I hope that those tips I gave you can help you to improve your receiving. And of course we can answer questions, and I think we're going to open Ken for questions right now.
Yes, absolutely.
What do you think? Is that a good idea?
Yep. I think so. Excellent, JC. Very good. Okay, I have a couple questions already, so we'll dive into these. But if you'd like to submit one, go ahead and do it now. And I realize we're at an hour, which is fine. We can continue going here for a bit, take some questions. So first one comes from Dean, and he's wondering about your thoughts on a K9 AY loop.
Yes, K9AY is a loaded loop. It's semi-directivity, and that's what matters, directivity. Don't pay much time digging into the front back and tuning the front back. It is a same directive as a U, as a flag, is a loaded loop, is a wire, right, with a resistor transformer. So if you go back to that part, when you have the single loop, you have the RDF, and that's what you can get in terms of performance. If you have like 7 or 8 RDF, I think we are almost there, if I'm not wrong, like here, right? You can have 2 dB increasing RDF, and you can have 4 dB in signal to noise ratio. It's great. You can hear things that you cannot hear on the vertical. So for myself, it was a big move. When I started using U's, and K9AY is a very practical way to put 4 directions together. Gary put a fantastic project there. You can rotate 4 directions. It's a small footprint. But you limit it here to 4 dB. If you phase 2, right, you can get into 10 dB. You can go almost the same kinds of performance. And if you put a 4 square of K9AYs, you can get up to 12 dBs. So it depends how we implement. But anyway, if you don't detune your transmit antenna, if you don't shield, if you don't put a preamp in a next to the radio protected with metal shield, you don't let magnet field, you're going to lose all that thing. So the implementation is 50% of the project, right? And of course, it's a limitation of space. If you can phase 2, it's a nice story. But if you don't have the space, it does not help. I hope I answered your question.
Okay, great. Next question. This is a good one. Comes from Scott. What do you do if the noise is coming from the direction of the signal you're trying to receive? How about using a DSP?
Well, that's something interesting. You only can amplify things that's above the noise of the receiver. So if you have things below the noise and you put amplifier, you get more noise, right? And the only place you can reduce signal to noise ratio is really in front of the antenna. So in the case, if you move for horizontal polarization, you have 30 dB attenuation on the vertical signal. And like if you go to a horizontal wireless flag, that's what improves a lot, because the vertical signal is going to see 30 dB attenuation front. So in front of the first preamp, you get an increase in signal noise ratio. Then your DSP can work better. But there is no way for you to dig, because any amplification adds more noise, right? And you can reduce the bandwidth, you can apply things, but you really cannot increase signal to noise ratio after the coax. When signal get into the coax, it's only degradation. It's only get worse, not better. So you really need to care of how you keep the pattern on your receive antenna. I hope I answered your question.
Okay, good. Let's go down to Brazil. Papa Uniform 3 Hotel Alpha Golf is wondering what's the reason for putting the antenna up on the tower? Are you decreasing the noise floor, increasing the gain?
Well, actually, that's a good story. I put horizontal wireless flag to clean the trees, right, at 30 feet, and I was doing really well. And then I started knowing that 9 mic QAX was copying my signal, and I was not able to copy. It was really in panic. I say, I want to do something. And I saw the project for horizontal water flag wasn't on the fence. Then I decided to try up. I did try before at 10 feet and 30 feet, and it was not really good. It was gain so low. But when I moved to 120 feet, it was a different game. I started hearing the guy every day on 80 meters long pass. And after 1 year improving the system, and that's the thing about the system, I was able to work 9 mic QAX and my new zone and a new country in 160. So it's really fighting noise. You need to find a way to fight in noise. No need to be that complicated. Like I told you, on 80 you can hit half of that with 60 feet or 15 meters or 18 meters. You can do really well against 80. You still can do better in 160 than you have with the vertical and the other antennas. But answer your question, you want to put higher as possible and bigger as possible. Okay.
Okay, good. Mike is wondering if you can explain in more detail why the horizontal water flag doesn't change its vertical plane pattern with the height above the ground.
Oh, okay. We can go there. So let's move that thing. First, it's not a dipole. It's not a Yagi. Most of those antennas radiate up and down, and the loop radiate on the plane. That's what a small loop. If the water flag start becomes so big, looks more like a cubical quad, then the signal instead going on the plane of the loop is going to go in the center of the loop. So just because it's a loop, you have this cancellation here. That's the first thing, and means every signal come right from the below or right from above is canceled. When you phase two together, 180 degree, so the signal coming from one loop exactly the same signal in the other loop. So voltage 1, voltage 2 exactly the same. When you phase 180 degrees, phase and phi, right? You cancel. The output is 0. So the only reason you have a signal is because the signal coming like 45 degree and reach that wire in a difference of time from the other wire. So this difference in time, the signal is not there at the same time. So V1, there is a delay on V2. So you imagine two side-by-side loops. Let's see if I can get that picture here. Yeah, you see the signal coming from the front, reach the first wire, then milliseconds the second, milliseconds the milliseconds. So that difference in milliseconds is really what makes the directivity. And that is the same. Doesn't matter if you are close to the ground or really far from the ground, the difference in milliseconds will be the same. So it's almost no change until you go above half wave, then you start seeing some nulls like the dipole. But normally half wave is like we talk about 240 feet on 160. It's really not practical, right? So that's why it's the way it works. It's a phased two loops in phase, and it is a perfect cancellation between them. I hope I answered your question.
Okay, very good. We've got a couple more here. Let's try to burn through these relatively quick. John is wondering, how small can a 160 HWF be?
Excellent question. Well, we're coming down one big discussion with Dr. Dallas Langford. He's a mathematician and a very enthusiastic SWR receiver. When we start discussing how small could be, you cannot amplify anything below thermal noise. So thermal noise or Johnson noise was the movement of the atoms as the limit, like minus 174 dBm. So when you have a small loop, the loop itself has its own temperature. And its own temperature increases when you have a small loop. So you're limited on the noise of the loop itself. That's why you see loops with very large diameters trying to reduce the resistance, try to reduce the noise. So you can go small a point that you get into the thermal noise. And then you cannot amplify anymore. Otherwise, you can just put a gain. Gain is easy. You just put more gain, but it's not really gain. It's signal to noise ratio. It's noise figure. You can drop noise figure to 1, half, but then you close to 100 degree Kelvin, very close to the equivalent temperature of the power noise, this cabin, and you cannot go smaller than this. So practically, if you live in a very quiet place, really quiet, middle of nowhere, we measure a 200 square feet loop is not limited in terms of thermal noise. You can copy almost everything on a very quiet day, almost to minus 123 dBm. So, but if you live in a city when there's a lot of noise, your noise is going to be the limit. So there is no point in have a bigger water flag if the noise is your local noise. So then you can reduce the size and get the local noise below the MDS, minimum detect signal of the receiver, that you cannot amplify. It means the size of the loop meets the size, the noise you have locally. If you live in a very noisy place, you can do very well with a small loop. I saw people using loops like 4 meters by 2 meters and have excellent results on 20 meters, 17 meters, right? Maybe you can go lower, but you need to raise the frequency. You cannot expect a 4 by 2 meters loop or a 15 by 10 to perform well 160. It's too noisy. The thermal noise of the loop itself and is more than you can amplify. So the signal will be really weak below the point of amplification. I hope I answered your question.
Okay, let's try to grab 2 more questions yet. For those questions I don't get to, I encourage you maybe to drop JC an email, and hopefully he can help you. But let's try to get at 2 more here yet. And Roger said, I only saw a brief mention of the pixel set magnetic loop at the beginning. How does it compare to the flag and or the K9AY? And you kind of mentioned the K9AY already.
Exactly. It's really RDF. Doesn't matter what you see people claiming, right? It's really about directivity. If you have directivity, you have increase in signal to noise ratio. So the magnetic loop is a little better than inverted V. It's right here. Sorry. I lost that thing. Let's see if I can come back to this. Oh, okay. Yeah, I think I lost my pointer here. Yeah, my pointer, I got it back. So here's the magnet loop. You have like 1.5 increase in RDF. It means 3 dB increase in signal to noise ratio. That's good. That's really good. You can hear better than the vertical. Also, magnet loop has a particular point where it cancels magnet noise or nearby structure. So there's a lot of noise that is shielded by the magnet effect of the loop. But you're limited on directivity. If you're going to increase and you're going to dig weak signals, you need to increase directivity. It's not about front, back, or sides, null the size. So you can have a magnet loop and do a AM broadcast in one direction and look the other, say you listen another broadcast, but does not help you to dig a weak signal out of the noise. The only thing you can get a signal out of the noise is increasing directivity. So a K9AY, you can hear weaker signal or impressively longer. The signal come out of the noise, stay up, and go back to the noise. If you have a magnet loop, sometimes you can hear the signal for 10 seconds. K9AY, YU or flag can hear longer, like 20 seconds. If you have a horizontal loop or a shared apex array near 10 dB, you can hear the guy for maybe 2 minutes or 3 minutes. That's enough for you to work at the X. And if you have like a beverage, or sometimes I hear the guy for 2 hours, 3 hours, and the other guy here with the loop just for a few minutes. It's really about directivity. Don't get full of cancellation deep sides, because it's just beautiful to watch, easy to measure, but does not give you any benefit. You're never going to work 300 countries with a magnet loop. You can go to 100, like with antennas close to 11, 12, you can work 100 countries every 2 months. Like on the marathon, I'm already 125 new countries on 6 starting in January. And my average is like 150 every year in the last 10 years. So if you have a loop, you can work the XCC in 3 or 4 years, but not in 2 or 3 months, because the time that the signal is above noise is big difference between how much time the signal is above noise if you have a more directive antenna. I think I answered your question.
Okay, last question, and this kind of ties into what you were just saying, so maybe you can just give a real short answer here to John, and he's wondering if there's a benefit to using the Waller loop at rooftop level.
Of course. Remember, anytime you're above ground and you cancel signal from ground wave, you have increase in signal to noise ratio. It allows you to receive signals that you cannot use with the vertical. Everything we talk here about the vertical and the more directive systems like a loop, a flag, allows you to copy signals where you don't have. And question before, takeoff does not change above ground. Doesn't mean if you are near the ground or far, it's ground independent. So that's the beauty of that thing, the small horizontal loops. Actually, if you look into a Beverage patent, RCA asked him to design an antenna for TV. So the original idea about a loaded loop was to receive broadcast TV and broadband in different channels. Otherwise, they come up with that solution specifically for rooftop. I have several friends with antenna rooftop and other installations pending. They're implementing, but the results is always good. It's not like you can cancel everything. You have noise coming too close. There is no really vertical. It's not really horizontal because there is no attenuation on the floor. Imagine that one thing is you have a perfect surface reflecting, canceling. Other thing you have city with cars and houses and things, and it's not the same, right? But it does help a lot. I think that's the answer to the question.
Okay, great. There are a number of questions here, but we've run out of time. So, JC, I don't know. Would you like to give out email address? Maybe if they got a question, they can just send directly to you.
Actually, you can send to jay@top-beam.com. JAY@top-beam.com. We spread. Jay is gonna spread between. Also works sales at topbeam.com. Doug and me or Jay can help you with your question for sure. And also just let you know, if you get the presentation, there's a lot of backup slides. There's a lot of other slides with interesting information. Then if you have any question about the other slide that didn't cover today, we don't have all the time, we really happy to answer those questions.
Okay, that's great, and that's at Top Beam. So JC, Doug, Jay, really appreciate you guys taking the time to put this together. A fantastic presentation. We had a wonderful group of people here, and maybe we can do it again sometime. There certainly is a ton of interest in this, so thank the three of you for your time. Again, just want to remind everyone that we have recorded this. It will be posted to the WWROF webpage under the webinar link, and I will try to get that posted this weekend if possible. And we'll send out a note reminding everyone once it's posted. So again, thank you everyone for your participation. Glad you could be here. Have a great weekend, and good luck DXing. Thank you all. 73s. Bye-bye.